One can learn about energy relationships and even chemical bonding by using dispersed light to study absorption and emission by atoms, molecules, proteins, minerals, and other substances. To apply this knowledge, one needs the concept of energy levels, discussed in previous podcasts, to interpret spectra, even the simplest absorption spectra. Emission is much more subtle, since it consists of both spontaneous and stimulated processes. There are also competing non-radiative processes, which we will ignore here for simplicity. We will focus on the most basic theory that accounts for absorption and the two types of emission, spontaneous and stimulated. Einstein's theory of quantum radiation focuses only on the radiative aspect of a transition between two energy levels. There are three types of transition: absorption, spontaneous emission, and stimulated emission. Spontaneous emission is intuitively understandable. If a molecule or material has received energy by absorption of radiation, it is promoted to an excited state. The excited state has excess energy. It is metastable, and relaxation will occur on a relatively short time scale. Spontaneous emission is typically a nanosecond phenomenon. Stimulated emission requires input of radiation energy. One photon interacts with the system, and two photons emerge. This process can compete with spontaneous emission if the radiant flux is sufficiently large. In a two-level system, the rate of absorption is equal to that of stimulated emission. There was a delay of approximately a decade between the introduction of the hypothesis of quantized radiation and a theory to explain atomic and molecular transitions. In 1917, Einstein took the implications of the Planck theory of quantization one step further. He recognized that the concept of quantum levels of radiation implied fundamental relationships between absorption and emission. While there is only one absorption process, there are two types of emission: spontaneous and stimulated. To explain these phenomena in a cohesive manner, Einstein used the thought process that had been successful in the photoelectric effect, which invoked a photon as the quantum particle of radiation. Here we show that the derivation of the Einstein coefficients for radiative transitions is based on the Planck model. The Planck theory assumes that all energy levels have the same fixed energy spacing equal to h nu. This means that the equilibrium and the transitions between any two adjacent levels is the same. There are also relationships between levels spaced by 2h nu, 3h nu, and so on, but we will not consider these. Further development of quantum mechanics shows that all allowed transitions can only occur between adjacent levels in atoms and molecules. We can select any two adjacent levels for the derivation of fundamental spectroscopic coefficients. To illustrate this, we have drawn a red rectangle that encompasses two of the levels. It does not matter which two of the levels we choose. As long as they are adjacent and separated by an energy h nu, their relative populations and rates of upward and downward transitions in response to external radiative flux will be the same. We can think of the relative populations as an equilibrium constant. The ratio of population numbers is proportional to a ratio of concentrations that you have seen in previous courses. N2 is the number of particles in the excited state, and N1 is the number in the ground state. Since there is only one state at each energy level, there is no entropy change in this system. Entropy enters a quantum system like this one when the number of states of identical energy is greater than 1, that is, when there are degenerate states. One wonders why the term degenerate became established in chemistry and physics, when isoenergetic is much more accurate. In any case, when entropy is not in the picture, the energy difference h nu is also a free energy difference. The equilibrium constant is the same exponential of negative free energy divided by RT that you have seen in previous courses. In this case, we are using units per particle rather than per mole, so the universal gas constant R is replaced by the Boltzmann constant K. Remember that these two constants are related by Avogadro's number. R is in units of energy per mole Kelvin, and K is in units of energy per molecule Kelvin. Realizing the implication that light can act as a particle, Einstein derived a fundamental model for absorption, stimulated and spontaneous emission from a two-level system. Einstein's model builds directly on the Planck distribution, and the radiation used in the derivation is the same as the Planck distribution itself. The insight that absorption implies stimulated emission is almost impossible to consider thinking only about light as a wave. We focus on two energy states in the Planck distribution, which we can call level 1 and level 2. 1 is the lower level, or ground state, and 2 is the excited state. In this two-state model, the transition rates for absorption and emission are W12 and W21, respectively. The energy spacing is h nu for any two adjacent states we could choose in the energy ladder. The change in population of N1 gives the upward rate of transition, which is the rate of absorption of radiation. The change in population of N2 gives the downward rate, which is the rate of emission. We can consider the system to be in equilibrium, as shown here, for equilibrium constant K. Since the two levels are in equilibrium, the upward rate, W12, is equal to the downward rate, W21. This is the principle of microscopic reversibility. This slide shows the two-level system with three possible transitions between the states. The two processes that require light are multiplied by ρ. Rho is the irradiance of the Planck distribution. The presence of ρ in these equations shows how directly Einstein derived the concepts in his theory from Planck's theory. There are two types of emission possible. Even in the absence of radiation, the excited state has a spontaneous rate of emission. There is also a stimulated emission process, which is just the absorption process in reverse with the concomitant emission of a photon. Light is required for absorption, but also for stimulated emission. The spontaneous coefficient is called A21, to distinguish it from radiation-driven coefficients, B21 and B12. In summary, Einstein defined three fundamental spectroscopic coefficients. B12, the coefficient for absorption, B21, the coefficient for stimulated emission, and A21, the coefficient for spontaneous emission. The B coefficients require radiation and would be multiplied by ρ, the energy density. The A coefficient does not require radiation. However, energy must already be in the system, since spontaneous emission can only occur from an excited state. The upward rate, W12, has only one term involving the absorption coefficient. The downward rate, W21, has two terms, one for the stimulated and the other for spontaneous emission. We can write an equation for a microscopic equilibrium constant, which is needed to fulfill the assumption that the system is in equilibrium. In this system, the energy difference, E2 minus E1, is h nu, given in the second line on this slide. The two rates are equal, which leads to the third line on this slide. Next, we solve for ρ. Note the color coding. The numbers in red are populations. The radiative coefficients for absorption and stimulated emission are in blue, and the spontaneous emission coefficient in purple. The absorption and stimulated emission coefficients are represented in the same blue color because we will assume that they are equal as we proceed. In other words, the coefficient B12 equals B21. This relationship is expected because the transition dipole moment for a quantum transition has the same value for an upward or downward transition. The transition dipole moment was defined using first-order, time-dependent perturbation theory by Paul Dirac in 1927. The square of the transition dipole moment that appears in Dirac's derivation became known as the Fermi-Golden Rule in 1950. This most fundamental calculation of the spectroscopic rate constant is directly related to the Einstein coefficients B12 and B21. Next, we divide through both top and bottom by N2 to clarify the equilibrium constant in the denominator. N1 over N2 is the inverse of the equilibrium constant we examined previously. This changes the sign in the exponent from minus to plus, e to the h nu over kt. This inverse equilibrium constant appears to have the same form as a term in the Planck distribution. It now becomes clear that the goal of the algebra has been to write the Einstein expression for radiation equilibrium of two states in terms that can be compared to the Planck model. The Einstein model for a two-state equilibrium is identical to the Planck distribution if B12 equals B21 and A21 equals 8 pi h nu cubed over c cubed times B12. This is an important result because it gives us a fixed relationship between spontaneous and stimulated emission, and it also tells us that absorption and stimulated emission coefficients are equal. Furthermore, in this fixed relationship between spontaneous and stimulated emission, it tells us that the spontaneous emission increases as the third power of frequency. The decay of the excited state by spontaneous emission follows first-order kinetics. By analyzing the exponential rate of decay, one can see that A21 is the radiative rate constant. It has units of seconds to the minus 1. It is inversely related to the radiative lifetime. Since this quantity can be measured using a time-resolved fluorescence experiment, it provides an important connection between theory and experiment. The decay of the excited state by spontaneous emission follows first-order kinetics. By analyzing the exponential rate of decay, one can see that A21 is the radiative rate constant. It has units of seconds to the minus 1. It is inversely related to the radiative lifetime. Since this quantity can be measured using a time-resolved fluorescence experiment, it provides an important connection between theory and experiment. Einstein's analysis also gives the first hint of how to build a laser. The acronym LASER is Light Amplification by the Stimulated Emission of Radiation. Such a phenomenon is possible, but not in a two-level system. Since the incident photon stimulates the decay of another photon, we have a system with one photon in and two photons out. That is, we have amplification. To use the stimulated emission to obtain a burst of light, we need a population inversion. We need much more population in level 2 than in level 1. However, at infinite excitation energy, the population of N2 can be at most equal to N1. To obtain a population inversion, one must find a 3-level or 4-level system. Nonetheless, the very idea that such a device is possible is implied by the relationship between stimulated and spontaneous emission in Einstein's quantum theory of radiation.